Hello, everybody, and welcome to the UCLA Meteorite Gallery monthly lecture series. Today, I'm pleased that we have as our guest lecturer, Mike Zolensky from Johnson Space Center in Houston. And we have a bit of a
there's a little bit of an echo, so maybe somebody needs to mute.
Me?
No, not you.
Everybody's muted but Kevin, Ellen, and Michael.
Okay, I was muted.
According to what I see.
I'll mute.
Well, anyway, folks, Mike has been at Johnson Space Center since 1985. He's, I found out today, a native of Rochester, New York, got his BS in geology at New Mexico Tech, his PhD in geochemistry and mineralogy from Penn State. He was a National Research Council postdoc at NASA JSC, and they recognized his talent and hired him in '85. And he's he had so much inertia, he's been unable to move ever since. He let me know that he was a 6th grade science award winner, which I guess was the highlight of his life. He had a few other awards like the Leonard Medal from the Meteorological Society, an award from JAXA and things like that. He told me that but nothing compares to being a 6th grade science winner. And he let me know that he shook hands in an eerie way with Stephen Hawking at one time. And I looked into the more details of that, but we don't have to share them right now. Anyway, his talk today is, do we already have a sample of Ceres? Which is an interesting and provocative title. So go ahead, Mike.
Okay. Okay. You can see that, right?
Yes.
Okay, great. Okay. Yeah. So I'll just say quickly that Lou Ashwell always told me that anytime a title has a question mark at the end, the answer is always no. So maybe, take that with a grain of salt also. And why isn't this advancing? My slides are not advancing now.
You may have to click back on your PowerPoint in case you were clicked on Zoom.
Back?
Well, click back in the window of the PowerPoint, and then it should advance.
Oh, you're right. Okay. Oh, wow. You're technical genius. Okay. So looking at the audience, you guys know all those already, but one question is, Ceres, I hope you can see my pointer here moving around, so pointer. Did Ceres form in place, or did it migrate from somewhere else after its formation, which is a pretty important question. And that's something that we kind of hope to figure out from the Dawn mission. Maybe we didn't, maybe we did. Now let's briefly mention that there are all kinds of models that indicate that the giant planets migrated after formation, and there's a lot of evidence this really did happen from the lack of KBOs and asteroids and the characterization of other star systems, other planetary systems where there are giant planets up close, nuzzling close to their host star. And they can't have formed there because there wasn't enough material to do that. They must have formed and then migrated inward. It's mostly a pretty common thing that the giant planets, once they form, they're interacting with planetesimals and the gas in the nebula, which tugs them in. And in the case of models indicate that in the case of Jupiter and Saturn, as they were migrating inward, when they crossed the 2-1 resonance, their eccentricities increased, which then pumped a lot of energy into the surrounding asteroids and KBOs. And some models show Neptune having formed well inside of those giant planets and then being pushed outward by this migration. And as Neptune then nozzles its way out through the KBOs to drag a lot of KBOs either out towards it or push them inward towards the sun. So the result is that a giant planet migration must have had a major role to play in moving volatiles from the outer solar system into the inner solar system. The question is, did those volatiles come in the form of large objects like Ceres, or only smaller ones? And we don't know the answer to that yet. But The presumption lately has been that Ceres formed out where the KBOs were, and then was pushed in its current place, maybe with most of the sea asteroids, in fact, after the giant planets began to form. And then when Jupiter formed, it further messed up the picture for KBOs and asteroids, depleting those areas even further. I think I already said this, and I stole this picture from the web, as you can see down below. So Dawn mission went to Ceres. It was a great mission. It observed that there appears to be all the ingredients for life on Ceres, including water, all the important elements you see in life, energy, supply. And geophysical data suggests the presence of extensive water ice and even the need for salts and clathrate hydrates to explain topography and recent volcanism on that body, which may be continued today. And Ceres shows extensive evidence for water ice, especially in explosion areas, stratovolcanism areas, and impact sites. And spectroscopy suggests that there are various types of carbonates and ammonium-bearing compounds, including biophthalosilicates, sodium chloride, and water-bearing sodium chloride called a hydrohalite has been reported in different sites across Ceres, especially in some of these impact basins and in some of these craters from volcanism. So there's these pictures of what Ceres might look like inside. And the cool thing is that there could well be subsurface ocean there, which is driving volcanism today. And that's interesting because if you could then either sample Ceres by flying through a volcanic eruption or land in one of these volcanic sites, you have potential for sampling pretty fresh material from the interior, which could include very complicated organics. And of course, that makes land mission kind of dangerous because if there's any kind of living material there, you have to worry about, deadly viruses coming and destroying us all. That's probably not going to happen, but it's still a very interesting possibility. And people have talked about a mission to do that, to land on Ceres, collect samples, maybe an Akator basin, and return with samples to Earth. That'd be a really cool mission. I wish someone would do that. But maybe you don't have to worry about that. Maybe there are already samples of Ceres or materials analogous to Ceres on Earth already. So briefly from the Dawn mission, the current picture of Ceres mineralogy is lots of magnesium, calcium carbonates, locally enriched in sodium, and also perhaps hydrated sodium carbonates. And keep that in mind later on in this talk. Magnesium and ammoniated phyllosilicates, again, probably serpentine and saponite, like in all the other meteorites we have. Now, I mentioned that, in fact, ammoniated phyllosilicates was first proposed by Trudy King way back in the 70s. And so it was apparently verified by John. And we haven't ever seen ammoniated phyllosilicates in any extraterrestrial materials. I'm not sure we should expect to see it because it would be interacting with the atmosphere so quickly, it'd be gone. But people have looked. We thought we might see it in the Ryugu samples, and we did not. But people are still thinking about it. Abundant magnetite, organics, especially aliphatic, sulfates, either abundant or not abundant, depending on which paper you read. And then finally, hydrohalides and/or halides also reported in some abundance in places like Akator crater. So, origin of Ceres, presence of these ammoniated compounds and abundant carbon suggests that Ceres volatiles formed well beyond the inner solar system, and perhaps even out way beyond most of the sea chondrites. However, the specific region is not unknown, obviously. And while it's possible Ceres formed in situ and accreted volatile material that was carried in by these planetary migrations. So Ceres could have formed out where the KBOs were and then pushed in during giant planet migration, or maybe it formed in situ from materials that were pushed in by that reshuffling. And Ceres shows many similarities to ocean worlds in the outer solar system, especially to Enceladus. And since there's some analyses from a spacecraft flying through Enceladus plumes, that's a really interesting thing to think about. And I'll come back to that later on in this talk as well. And anyone who wants to test a possibility of living organisms having arisen on Ceres, you want to go to Akator crater and land there and check it out. And I've seen proposals to do that, although of course, credit protection requirements would make that a dicey thing to do. It would be very challenging. And furthermore, Ceres is there likely a representative of the population of materials that brought organics and water to the inner solar system, including Earth. And so it's interesting from that standpoint as well. So it'd be nice to know exactly what the mineralogy of Ceres is, but that's probably going to require a sample return mission, or at least a very sophisticated analytical suite on a landing mission. But this talk is just quickly exploring the possibility that we already have things in meteorites that are analogous to Ceres, or perhaps from Ceres itself. So quickly, you guys are all know meteorites. We're talking about organic volatile-rich materials are going to be down here in the carbonaceous chondrites for the most part, but to some degree also in ordinary chondrites, and interestingly also in uralites, oddly enough, and I'll come to that as well. So I'll skip over these slides. Okay, so I'll just go back quickly since I showed these. These are just two slides that quickly, briefly talk about the observed mineralogy of materials in the major sea chondrite types, and they mostly share the mineralogy of Ceres. You have lots of phyllosilicates, principally saponite and serpentine, although no ammoniated phyllosilicates, but then they wouldn't have been preserved. Abundant carbonates, sulfides, sulfur, lots of magnetite in most of these guys, even the CV chondrites. And how about halite? Well, halite actually was reported in Murchison back in, I think, 1981. And I'll show a picture of that later on in my talk. People kind of ignored that report, but it was valid, I think. Moving on to other meteorite types that contain volatile materials, in particular the rhyolites and the ordinary chondrites. The rhyolites, again, mention in just a minute, rhyolites themselves, no, but there are commonly xenoliths of sea chondrite material in these. These are very interesting, and I'll come back at just a second. And finally, there's several reports of, there's obviously sea chondrite xenoliths in many H and LL chondrites, especially LL3s. They're not all CMs like was thought a long time ago. There are all kinds of things there. And then, of course, we have several meteorites, three ordinary chondrites with abundant halite. So let's go on. So, this is some of these sea chondrite class. They're often in all kinds of the meteorites. In the HEDs, they're most commonly CM chondrite material. But the small ones sometimes include some C1 material, which might or might not be CI. It's always been clear to me that CM chondrites are common as xenoliths in so many types of meteorites. I've never yet seen, at least I've never seen a xenolith in a CM chondrite. And anytime I've seen reports of that, or thought I found one myself, it's always turned out to be later on either an unusual chondrule, or in one case, a large metamorphosed CM chondrite lithology. So that's probably had to do with the strength of the CMs being so weak that material smashing into it just breaks them apart. And then those little pieces end up all kinds of places in the solar system. But this is very interesting, I thought. And I mentioned this before, the HEDs sometimes contain, some of the HEDs, particularly the howarites, contain a small class of things that look a lot like CI chondrites. They've been variously, here's one here. This is in well-known Yamato 791834 eucrite. They're in dioxanites too, by the way. And most of the opaques you see there, the bright white phases there are magnetite. There's some sulfides there as well. But it's mostly saponite and serpentine and carbonates. And these tend to be very tiny because they're very, very friable, but they're present in many of the HEDs and deserve more attention, I think. More interest here are the sea chondrite class found in rhyolites. And these aren't present in most rhyolites, but they're present in a lot of them. In some cases, they're actually quite large. And that's been recently studied by Serena and Marcus Patzek, and others are looking at these in more attention lately. And there's this one here. And here's another one, a BSC view of one in Darwagani 164, which again consists mainly of phyllosilicates, a lot of magnetite. That's mostly what you see there in white. Some sulfides, carbonates, like the one here. This is a This is a carbonate here, phosphates. So it's definitely a C1 mineralogy, whether it's CI or not, I don't know. But these are fairly abundant in some uralites, which is interesting. So I mentioned earlier that we talked about halite in ordinary chondrites, but halite's not just for ordinary chondrites. It was reported back in 1978 by Jack Berkeley in several uralite falls. So he had freshly broken open in his lab, and he found potassium and sodium chloride as discrete phases in these. Probably no one believed this, and I talked to him about it years ago, and he believes he's right. No one's verified this, but isn't it interesting that you see salt in uralites and also see chondrite class in uralites. And then, as I mentioned before, Dave Barber, who's an excellent microscopist, found halite and sylvite, potassium and sodium chloride crystals in Murchison and E1. On the right, you see a TM image, and the halites, these spaces right, little crystals here, said they were enclosed in kind of a waxy organic material, which protected them against microtomy. This is a crushed sample. This is pre-microtomy days. You just take the sample, crush it, and just burst it on a TM grid. And so it's just a thin area there. So the waxy material, he thought, had protected these against everything that happened to the sample before he observed it. So no one's, to my knowledge, has observed halite again in the CM chondrite, but it is interesting that here it is. Probably people just have looked past it and not observed it. So again, there's these famous observations of halite in two ordinary chondrites, Zag and Monaghan's, more than 20 years ago now. And the cool thing is that halite is a really cool mineral. You can date it, and these were dated by several techniques to be 4.5 billion years old. It has a freshness indicator, which is the color purple and blue from a radiation damage, accumulated radiation damage. Had these crystals been formed on the Earth after the fall, had they been dissolved during sample preparation and then reprecipitated, they would not have had these bright colors. So the bright colors are basically attract your eye to the sample and demand that you observe them, but also indicates that they're still fresh and not contaminated very much. So as long as you're very careful how you handle your samples, we expected to find a lot more of these by now. One was that's reported in our discussion earlier. One has been found now in a third ordinary chondrite. I'll describe that again in a few minutes. So the cool thing about this was that both the halites in Monaghan's and Zag have fairly abundant aqueous fluid inclusion, and they're easily observable in your lab. And if you see vapor bubbles floating around in these, this is the coolest thing ever. And you know these are not terrestrial fluids because again they're in these purple blue halites, so they can't have been dissolved on the Earth. I guess someone could fake these by taking halite like brine and dyeing it blue or purple, and then putting it in the meteorite, right? I always kind of thought maybe that's what's happening, but when these were dated to 4.5 billion years, that idea went away. So I've always kind of wondered when I hear about this, maybe someone making these, but that didn't happen here. And maybe you can see this is a bubble floating in this one fluid inclusion here. This is in Monaghan's. So there's a whole bunch of these fluid inclusions here. And then we're lucky to see a vapor bubble moving around, which tells you that's still fresh and full of fluid. There's one here too. Hope you can see that. And I might add that if you want to look at fluid inclusions in your lab, a smart thing to do is take your sample, don't prepare it using any kind of fluid, right? Put it in a freezer and leave it frozen for a while, and then take it out and immediately look at it in very low light conditions, because as your microscope heats up the sample, these bubbles, the fluids expand and bubbles contract and disappear. And within a few minutes, some just seconds, bubbles gone, and all you see is a little thing that you can't tell if it's a fluid inclusion or not. And so a little trick there for looking at fluid inclusions, keep a freezer handy, and I can describe that more later on if you want to hear about that. Oh yeah, so within the last couple of years, there's this new cool meteorite with the catchy name CD El Habib 001, where people have found it's got pretty abundant purple halite. And there was a talk about it last week at LPSC, pretty cool talk. Unfortunately, it looks to me like this sample was fried What I mean is the halites don't have any fluid inclusions, and they have very irregular kind of serrated outlines. Which means I think that the halite was incorporated into the ordinary chondrite regolith while it was still very warm, maybe during retrograde metamorphism. And the heating caused the fluids just to race out of the halites. And then once they reached the edge of the crystal, then the fluid was in contact with the surrounding rock and caused alteration there. And so that would deprive the halites of fluids. But if there could still be solid inclusions in the halite, it could also be C chondrite class in these samples. So these are definitely worth looking at. The abstract suggests that these are formed from fluids indigenous to the ordinary chondrite asteroid. I tend to think that they're exogenous, they're xenoless, but they've interacted with the regolith for sure. So again, I would thought by now we'd have dozens of these meteorites with halites, but just one more after 20 years. That's pretty piss poor. Sorry, not your fault. One cool thing is Richard Norton found this C chondrite clast in Zag many years ago, and I managed to. I was very nice to him, and he gave it to me. I can't believe this, but no one's found one since then. And this class is quite large. And I've only to this day only looked at a tiny sliver of it. Most of it's still sitting in nitrogen cabinet, and it deserves a lot more attention than it's gotten in the past. And we'll see why. So here's the only polished mount we ever made of this, of a little piece of this, a really tiny piece of this class. Again, most of it's just sitting in nitrogen. And what you can see here is looks like all these C chondrite class and uralites and the real fine small grain, fine grain small ones and HEDs. Lots of phyllosilicates, serpentine plus saponite, no ammoniated saponite, but then no one looked. It's probably gone by now. The big guys here, the big opaques here is the BSC image, are sulfides. Almost all the small ones are magnetite. There's some phosphates. There's these dark things here are actually grains, organic rich grains, not holes in the sample, and including organic nanoglobules. And organics are a big part of the story here. And there's big carbonate. This one is almost a millimeter across. This big carbonate, pretty cool. And here's why. The sample also contains halite. So this is in Zag, which contains halite, and the C chondrite class in Zag also contains halite. So this is the halite here. So it's pretty definitive that the halite is accompanying the C chondrite material into the ordinary chondrite parent body. It's exogenous. It's not from EV or some other ordinary chondrite parent. Here's cool. This is this big carbonate in just one polished section, this polished mount we made, which we made without fluid because I thought, you know what, I had something like this appearing. This is a multi-lobed, multi-grain dolomite. And here's a element map. I made this last week. I put there last night, actually. And the cool thing is, there's sodium, the lower right. You see the sodium, some sodium phase concentrated around these carbonate grains. And remember that there's sodium-rich phases found on Ceres, either sodium-bearing carbonate or some other phase there. I don't think this sodium is in the carbonate, but it's associated with the carbonate. Another cool thing is that these, you can't see it very well. I don't show it here, I'm sorry. But the cores of these dolomites are enriched in manganese. So they're low in iron and enriched in manganese in the cores. So the dolomites, multi-lobe, these little holes here are from probanalices, but there are in fact tiny little holes on the surface which suggest that there are preserved aqueous fluid inclusions in some of these. So what we're going to do very, very soon is probably fib out one of these grains, look at it by top sims. But you know, I should probably also take the rest of this class to do X-ray CT on it and see what else is in the class, because it's a pretty cool class. Here's one of these organic nanoglobules. Again, this is all about this Zag class. This one's only a few microns in size, but there are larger grains of organic rich material as well, going pretty fast here. One of them was fibbed out by Yoko Kebukawa, and she and I was looking at the organics in here by Zane, carbon zanes, and all kinds of techniques, Raman, and it's a pretty complicated organic story. And that's being written up in papers by Yoko and her collaborators right now. Also, Queenie Chan found amino acids in this sample, probably indigenous to the sample. Also, Moto Ito has been doing nanosims analyses of grains from this class. And this results of nanosims by Moto Ito and Yoko Kibakawa of this same fib sample. And the cool thing is that there are correlated excesses in heavy nitrogen, carbon, and oxygen in the same grains, which is a little bit unusual. So very unusual organics, pretty cool. These are pretty common in this class, and you see the scale bar. It's a 5 micron scale bar. These aren't really tiny class of organics. They're quite large. They're pretty abundant. So this is the Warren diagram. You guys know it very well. You probably can't read the top here very well, but there's this progression from CO chondrites down here up to CV, CM, CV, CR to CI chondrites as you increase the amount of heavy oxygen and chrome. And there's all kinds of interpretations of what this diagram could mean. And one interpretation is that, well, gee, we're getting more water and organic rich as you go in this direction, this arrow. So maybe this is indicating increasing heliocentric distance of formation. I mean, it's just one idea. By the way, last week I saw a talk where someone had to divide these into 3 groups now. There's NC, CC, and then CI group. And this Ryu group pops up here with the CI chondrites. So I'm not sure how happy you are about that, but I saw that in a talk last week. That was kind of interesting. When we measured the data for the ZAG class, the plots here. It's even heavier than Orgade, CI chondrites, which I thought was pretty cool. We kind of thought that would be the case, actually, based on the high organic content and the oxygen content we knew. So if this is really telling us about heliocentric distance, I'm not saying it is, again, is consistent with this class having formed, maybe out beyond where most of the C chondrites are forming. Okay, back to uralites. You all know about Almahatasita. It fell. This is an old slide from like 10 years ago. Hundreds of stones found. I think probably more than a dozen different meteorites included together. Maybe something like 50% for 60% uralites, 4% other things. So this was a material that, when the rhyolite parent body broke up, either reaccreted with other materials, maybe this material is what broke up UPP parent body to begin with. In any case, you have like a beanbag asteroid consisting of mostly rhyolite material, all kinds of rhyolite material, by the way, with all kinds of ordinary chondrite materials, EHEL, R-like materials, a lot of insight chondrite materials, by the way. Several kinds of ordinary chondrites, and then I've seen maybe 6 different C chondrite lithologies from this as well. Several C1s and then 1 CB. And it fell together, and you wouldn't have known these are related, but people measured the exposure history and realized that's what's going on. Pretty cool. Makes you wonder how often meteorite falls consist of more than one kind of meteorite. You just don't recognize it, of course. So again, thinking about the fact that you realize often contain C chondrite, C1 chondrite class, no surprise that there are several of these now found in Almahatasita, and this is 91A, and there's several others. Some goofy element map here on the left. Basically, the same mineralogy has been seen for the past few minutes here, mostly phyllosilicates, saponite plus serpentine, and back down the right here, this little red thing at the bottom here is, I think, pure saponite, pretty much, with some sulfide crystals inside there. Lots of magnetite, a whole lot of magnetite, complicated carbonates, including zone carbonates, dolomites. I'm not sure I've seen much calcite, but also magnesite, even some very iron-rich carbonates, phosphates, sulfides, similar story now. And here's where these guys plot, these 2 of these plot on the Warren diagram, even heavier than the ZAG class. So again, these things are mineralogically basically identical, except for the occurrence of halite in the ZAG class. So maybe these are, well, I'm suggesting that these are, if not from Ceres, then from something that's seen as the same processes and the same strong materials and same processes as Ceres did. So there are some other cool things going on here. You hear your talk next month is by Mark Fries. Mark and Steely are looking at a sample of the Monahans by Rahman at GeoVis Lab, and they found lots of solid inclusions in the halite, which I hadn't seen before. Yoshi Yamamoto had noted them in there. I just sort of skipped over them. And so we dissolved the halite crystal, one of the Monahans crystals, and started looking at these by Raman and TEM. And it's amazing what you can find. This is in one crystal, 8 small halite grains, mostly from one crystal though. It actually is Monahans, not Zag. It's yielded all these minerals. A wide range of olivine, mostly forsteritic, but really a wide range of it. All kinds of feldspars, these 2 kinds of pyroxenes, including high calcium pyroxene, phosphates, but mostly organics. I mean, most of the grains are organic dominated, including silicate that contains halogen substituted methane, metal, which might be contamination, pidocrosite, probably rust from the earth, maybe magnetite, sulfides, diamonds associated with carbonates. And that's kind of weird. Anyway, definitely not H. chondrite mineralogy. Again, it's consistent with C. chondrite derivation. So the idea is that these are grains from the rocky mantle and the fluids, the brines that were charging out through the parent body, just grab these little grains and they risk of floating around in the solution when the halite form. So these are samples of the rocky mantle, whatever object this halite formed on. And then here's this is a Raman pattern, which suggests that there's grains of chlorine substituted methane in the halite. So this is some kind of methane-bearing compound, organic compound, that was trapped in the brine. And when the halite crystallized, there's some chemistry going on there, right? Basically, it trapped a memory of methane, rich organic grain that was trapped in the brine. And this is cool because these things have been observed in Enceladus eruptions. So I'm doing another interesting link between materials in these halites and outer solar system volcanism. Let's go on here. So more than 10 years ago, Yamamoto-san and Shoichi Ito measured the hydrogen and oxygen isotope compositions of individual fluid inclusions in Zag and Monahans halite. And these were, heroic measurements to make at the time, and still really. But what they see is that there's quite a wide range, even in single crystals of halite, it's suggesting that the fluids are varying in composition by quite a bit. And they just indicate in this diagram that one interpretation is to have mixing between water you see in C. chondrite phyllosilicates and water that's seen in comas. But other interpretations are possible. The cool thing is that this shows you why it's important to measure these inclusions, these fluid inclusions, one at a time by this technique, because you're looking at quite a wide range. And one of the things I like to do is look at these carbonates that contain fluid inclusions and zoning, chemically zoned ones, and mark across the film, looking at fluid inclusions, compositions, and see if they change as you go across from one, say, iron-rich area to a magnesium, manganese-rich area, and then track how the fluid changed in composition during aqueous alteration. That should be possible. And so lately we started doing this at the University of Texas. I'm working with Andrei Dolikan, who's this crazy Romanian guy, and Bob Bodner, my longtime collaborator, looking at initially just the compounds present in aqueous fluid inclusions in Monahans and Zag. And then this summer they're getting new top sims, which will be able to do oxygen, hydrogen, and carbon isotope measurements on individual inclusions as well. So the deal is we put the sample, a very small sample in, freeze it to -140, that's about as low as we can get, sputter down and expose the inclusions one at a time, and then measure compounds that are present there. I'm not really a SIMS person, I'm a mineralogist, so I'm always very impressed by this technique. But there's also a lot of problems with top SIMS, it's very hard to interpret the results, but that's what we're doing. This is the first inclusion we found in Monahans. This is about 4 years ago. There's a beautiful fluid inclusion, a bubble you can see. And then here's the top SIMS, you see sputtered down to open that up. And the cool thing is you can definitely see OH here from water, nitrogen-bearing compounds. and lots of organic bearing compounds as well. That should have been a surprise, but it kind of was. These are brines. We can measure some chlorine, obviously, but also fluorine in these. We thought we'd see lots of calcium and iron. We really didn't see a lot of that. So we thought we'd see, when we froze these fluid inclusions years ago, we did look at the freezing and heating characteristics. The freezing temperature of the fluids indicated that there was some highly charged component in the fluid, and we thought it would be calcium or iron. It turns out there's organics there. They're probably affecting the freezing conditions more than these cations. So that was a little surprising. We continued on doing this. This is another large inclusion we analyzed 3 years ago. This is for a pandemic. This one contained all kinds of things, sodium obviously, but also sulfur is pretty cool. These are actually brines that contain rather a lot of sulfur. But the main thing is lots of organic bearing compounds, a real zoo. And these were negative bearing compounds. Now in tough sim, if you're breaking the molecules apart, you're looking at pieces of things. And if you're a good organic chemist, which I'm not, you try to piece it back together again into what the compounds were before you throw them apart. So whether that works or not, one important point here is that you can analyze some components in these fluid inclusions one at a time, determine which ones actually contain water, and you also can determine that they contain lots of organics. Whether you can decide what the organics are or not, that's sort of beyond my knowledge scale. But here's some of the positive, in the positive mode, some of the compounds we found. We did see some iron, not a whole lot in there. We see a lot of calcium. We didn't really see a lot of that. There's some potassium, obviously, no surprise there. But again, lots of organics. It's pretty cool. So, halite's a great thing to look at because there's no oxygen in the halite necessarily. So when you see OH, you're looking at water basically. Carbonate's harder because you have carbon there already. So when you see carbonated compounds, your question is, are you looking at the calcite or are you looking at organics in the fluid? We also done some inclusions in a Ryugu sulfide, iron sulfide crystal, which was reported last year. And that was really cool. Of course, the problem there is you're looking at a brine in sulfuric acid mixture. So that kind of swamped out a lot of the compounds. But even there, we saw lots of organics in that fluid as well. So there in the Ryugu, which is a CI chondrite basically, in Ryugu sulfide, the fluid that was making that pyrrhotite crystal was a brine also. We could see fluorine, chlorine, and it was a briny sulfuric acid compound, but also loaded with organics as well. So we're seeing organics in all these fluid inclusions, which is pretty cool. So this is the top sim results we've seen to date on a few Monahan's crystals so far. And in Monahan's, the halites have the biggest fluid inclusions, but they're not very common actually. They're kind of dispersed. In ZAG, the fluid inclusions are much more abundant, but they're really tiny. So we've avoided doing ZAG for a while. But you can see a wide range of these, again, there are pieces of things, pieces of compounds that are present in the fluids in Monahan's fluid inclusions. Okay, so I think I've already said all this. Yeah, there's a suggestion that some of these organic molecules may have been amino acids. Queenie Chan found amino acids in ZAG and Monahan's halite, which he thinks are indigenous to the halite, not just terrestrial contamination. And a suggestion that could also be present to some degree in these fluid inclusions. Remembering these things have been, they've been sitting in radiation damaged halites for 4.5 billion years. But these halites are purple and blue because of radiation damage. Basically, it's beta decay of potassium-40, same electrons around. So it's kind of amazing that unique complicated organics are present in the original state after all that time. They must have been reacting for quite a long time. Also, hydrogen would be leaking out of these inclusions through time as well. The oxygen is going to stay put, but hydrogen is pretty mobile. So things like measuring the pH of the solution, that's probably off because hydrogen will be leaking out of the inclusions and interacting with the rock. So we're making these great measurements, but you have to bear in mind that these halites, other rocks, haven't been immobile for 4.5 billion years. There's been some chemical reaction going on during this time. change things. So that's always something in the back of our mind. Main thing is that we can use topsin to do these analyses. That's pretty cool. We've already analyzed by this technique and measured fluid inclusions in carbonates, sulfides, and halides, not oxides. We plan to do oxides as well. And also phosphates should also be loaded with fluid inclusions. Those were reported back in the 80s by Ed Roeder, who was Mr. Fluid Inclusion. And that was reported in the Pete's chondrite. And no one's followed up on that since in all this time. And it's quite possible that there's a whole story there for the phosphates, which is recorded by Aqueous Fluid Inclusions that no one's looked at yet. We'll throw that out there. So to come to a conclusion here, do we already have samples of Ceres in these halites in ordinary chondrites and the C chondrite class in ZAG and the soluble C chondrite inclusions in Monahan's halites? Personally, the only way to test this hypothesis is to do a direct sample return from Ceres, I suspect. But we're doing additional characterization of halite inclusions to, again, in the future, to include more stable isotope analyses to help constrain the origins a little better. But if these samples really do sample Ceres or, again, analogous materials, then Ceres must have been cryovolcanically active soon after its formation, because these samples are 4.5 billion years old. Obviously, Ceres distributed large amounts of light organics around the asteroid belt in the inner solar system a long time ago. So was the cryovolcanism due to isotopic heating of an ice-bearing precursor? These carbonates we found in the ZAG class, I think they're potentially datable if we can figure out a good calibration for dolomite, because there are areas in there that are have quite wide-ranging composition, including manganese-rich, iron-depleted carbonates. I think that's and they're also quite large, almost a millimeter in size. So it must be an attractive target for doing chronology. And finally, a substantial amount of ice is obviously present in Ceres orbit at time of accretion. So most have formed, I think, probably out in the outer solar system and migrated inward. It's my own personal idea there. And if that's true, then Ceres and rocks, halites, should be present in all kinds of other brecciated meteorites, not just rhyolites and CM chondrites, but maybe more widely dispersed than that. So we should continue to keep our eyes open for unusual things in meteorites, and continue not to cut them using water and oil and diamond saws, but maybe break them open first and take a look inside. Or we've tried doing X-ray CT to find halites in ZAG samples. It didn't work very well, but as techniques develop, it should be possible to do that. And that's all I'll say there. So I'll just stop by acknowledging a lot of support for years and years by various NASA programs, most currently NASA's Emerging Worlds Program, and Ev Gibson, Ed Thompson, Richard Norton, and people of Monahan, Texas, for these great samples. And I'll stop there. Thank you.
Well, thank you very much, Mike. That was fascinating. We appreciate your giving us the talk. So do any of you guys online have questions? Just either raise your hand electronically or just unmute yourself and shout it out.
Oh, yeah, a question of you're not recommending cutting any meteorites with a diamond saw and a liquid, but just looking at freshly broken surfaces?
Yes, I mean, diamond blade, I mean, you can use diamond blade very slowly, cutting it, but then you have to accept the fact you've got diamonds embedded in the sample or carbon or something else in there.
Yeah.
And I do that anyway. I mean, you have to polish it somehow, right? To look at the sample, you just have to admit that, anytime you find little diamonds in your sample or something else, alumina grains, well, it's polishing. But fluids are out. I mean, if you have to use a fluid, I guess the only thing you should use is probably really, really pure ethanol. A brand new jar of, 200 proof ethanol with no water in it. Because the minute you open it up, atmospheric water gets in there. And so I have is new jars of pure ethanol. They open up and use once, and then give it to somebody else, right?
How about
using
kerosene?
oil? Pardon?
How about kerosene?
Bob Bodden recommends not using kerosene or any kind of oil. If you go back to the early 80s, there are these reports of fluid inclusions in lunar rocks and all kinds of meteorites. I didn't mention that. Bob and I are writing a paper right now on how to recognize fluid inclusions. But if you go back to your early, for those who are old enough, back to the early 80s, there were these New York Times front page reports of fluids found in lunar rocks and some meteorites that all turned out to be polishing oil and kerosene and water from cutting fluids. And you know, it took some brave scientists to admit they were wrong and write papers that said, no, this paper was incorrect. So even kerosene maybe is out. I mean, we're finding fluid inclusions loaded with organics. So if you're cutting your sample using kerosene, then you know, sure, you're compromising the sample. You don't have to. You can just cut it really slowly dry with a diamond blade and just accept the possibility of diamond contamination. But I would use no fluid unless you really have to. Then I guess ethanol, like I said.
Any additional questions for Mike before I ask questions?
I think David had his hand up. David Michaels.
Oh.
Nope, maybe he took it down.
Steve.
Steve's
Quick
got
question,
something.
what's the typical range of sizes of the halite crystals?
Yeah, they're the biggest ones I've seen are like a centimeter size. The British Museum has a huge one in Zag that's about a centimeter in size, down to as small as you want. I had a kilogram piece of Zag that I kept nitrogen for like 10 years. And in my postdoc, Queen Chan, we broke it up in the lab, in a clean lab, using pliers. Every break, we found more and more halites down to as small as you want. So up to centimeter size, down to, you know, very, very tiny.
So I got a 10 kilogram chunk of Zag.
Yeah. Don't lick it, right? I mean,
Don't lick it, right? Okay. Don't
you know,
wash it.
I kept this kilogram piece that I had in nitrogen for 10 years. It was fine, but ET gave me a piece he swore was like also maintained very cleanly for 10 years. I found nothing inside. So it all depends on how it was stored and your luck, because it's only in the gray, you know, brecciated matrix part of the meteorite. It's not in the dark or white class. So it depends on what your sample consists of. How you count was kept.
That actually explains a lot, because the pieces of Zag I got from ET, I didn't see any halite in it either.
Yeah, well, the ones I got from him, first on had lots of halite. And again, I thought, gee, it's this guy. I didn't know him at the time. I thought maybe he's like selling me manufactured halite. But once they were dated, we realized, no, that wasn't the case. You know.
Okay, Steve Desch had a question.
Yeah, this is so fascinating, Mike. I really like this topic, and thanks for bringing all this together. I have questions about how these get into these objects. I can understand clasts, but I can only imagine ejection of clasts after thermal evolution and implantation of Ceres. That takes tens of millions of years. I would think 60 million years. So my one question is whether that seems reasonable to you. And the second thing is, why are so many clasts in H5s in particular, and how do they get in there?
Yeah. So the first one, sure. I mean, I'm not an expert on dynamical mobility of materials, but you know, the dates we have had huge error bars. So dates on the halites take with a massive amount of massive grain of salt, right? But yeah, that's fine. And I think they had to have landed in big pieces of sea conch material, which then broke apart upon incorporation into the H chondrite regolith, and then halites just popped out. And this one Zag class is, you know, the remaining piece, a surviving piece of the original material that has halite in it. So the halites we have are just the surviving tiny little scraps that must have been huge impacting objects that are mostly destroyed, you know, like you say. What was your second question? I'm sorry.
Something special about H5 instead of H4?
I don't know. It's weird. Well, Zag is actually H3 to H5, I think. I don't know. It's clear. It's not in. It's only in 3 though, so that's still low numbers of population. But yeah, it's very clear. Maybe it's just a rare event that happened only once. It landed only in this one on Hebe, which is the presumed parent body of the H chondrites, right? Maybe just a rare occurrence, happened only one time, more or less.
A plurality of H chondrites are H5, so that may mean something.
Yeah.
Mike, I wanted to ask you, those guys who talked about that new sample were talking about sphalerite as well.
Right.
Did you see any sphalerite in?
Yeah, no, but there is sphalerite in Bill 2. And sphalerite's a well-known material for fluid inclusion work. And it's a pretty stable phase. It preserves fluid inclusions very, very well. So I bet they may, even though the halites in their study may have had no fluid inclusions, they should go back and look at the sphalerite. That's pretty cool. Don Brownlee had a question too.
Yes, Don? You have
Oh,
to
you're
unmute.
muted, Don. You're muted. You're still, yeah, okay, yeah. Now you're muted again, yeah. Still can't hear you.
Don, unmute yourself.
Or you can possibly hold down your space bar. There you go. Okay, now move your mouth.
Still can't hear you.
Can't hear you. If you want, you could type into the chat box and we could read it out.
Sorry, Don. Can't hear you at all.
We want to.
Don, oh, there he goes. He's,
No.
no.
I have a question while we're
Try
waiting for
again, try
Don.
now. You seem to be unmuted, but maybe your microphone's not working.
Oh, there you go.
There, we heard something now.
Almost, you still sound like a demented robot, but a little bit better.
Well, you can hear me at all.
Yes, now we
here you
can.
go.
Yeah.
I had two brief questions. One has to do with cutting fluid. And I asked him like this 2 days ago, but I asked him again. Freon, you're about to use 1,000 gallons of freon. But the second question is, how many Ceres could there get?
Yeah, I
Don,
couldn't
Don.
understand the question.
Don, your internet's breaking up. Maybe type the questions in the chat.
Oh, I'm sorry.
Anyway, Mike, maybe Don can type those in, but in the meantime, there is fluorine and chlorine in ordinary chondrites and ensitite chondrites. They reside presently mostly in the chondrules at first, and then during metamorphism, you get like an ordinary chondrite, you get chlorapatite, and then ensitite chondrites, you get various other strange compounds. We also see lawrencite in ensitite chondrites, like Klaus Kyle found it coating silica grains. So do you think that the fluorine and chlorine in these non-carbonaceous chondrites could be some salt that migrated in from the outer solar system?
Yeah, I mean, like I said, imagine these little halites surviving themselves, impacting into the ordinary chondrite regolithism is pretty hard to believe. It must have been a large object that contained lots of these halites, and it would have supplied quite a bit of then, sodium chlorine, fluorine, when it did, and probably most of it was destroyed on impact. So yeah, that's a good idea, I think.
Well,
and years
except
ago,
that if we see them in chondrules, it has to be pretty old, and that wouldn't work.
yeah.
So, so Don has put two questions into the chat, which I think are unrelated. First one is, what about Freon? Which I assume means as a
right.
as for
Yeah,
a cutting
That's
fluid.
right. Yeah, and I asked that question. So we can't use Freon in our lab. And as Don and I discussed last week, years ago we used Freon all the time to clean things in the cosmic dust lab. And then when Freon became a forbidden chemical at NASA, we actually hid like a 5-gallon can of it in the back of the cosmic dust lab for years and years. And then finally used it up pretty much, or we got rid of it. But yeah, I mean, I guess you could do that. We didn't try Freon. So if you wanted to use some fluid, I guess you could try Freon. That's right. Yeah. How hard is it to get Freon now? Is it like cocaine, really hard to get, or is it easy? Or I have no idea. I mean,
Well, here in LA, cocaine isn't that hard to get.
Yeah, I should,
I'll remind
please
you
check in
all,
that for me.
I'll remind you all that this is being recorded.
I didn't mean you'd know about it. I was just wondering idly, right? So yeah, I mean, there are probably other clever ways of using fluids that aren't going to contaminate the sample very much. We frankly, we can get a good enough polish, just dry, to do tough sims and sims work without using any kind of fluid. It isn't that critical. And the halite crystals, they break anyway. They have perfect cleavage. So you just basically press them into indium, and then you're set to go in the sims. So we don't have to resort to that heroic thing, I think.
Okay, let me interrupt. Don had another question and it was already answered by Steve Dash. So Kevin, you want to read those questions?
Well,
and
I was gonna offer Steve the microphone to answer the
Okay.
question. Or elaborate or have a discussion.
Oh, sure. I didn't want to interrupt, but sure. How many series could there have been? It depends on whether they were implanted and then the asteroid belt was depleted. But I don't think there was much depletion. I think probably what we see is what was there. But I think the secret is that maybe more of these largest asteroids could actually be implanted than just Ceres, and Pallas is orbitally dynamically favored to be like that.
Oh.
So I think Vesta is probably the largest really actually formed in the asteroid belt, and 15 Eunomia is one of them too. But many of the others, Hygeia and Juno, maybe Pallas, Ceres, definitely seem to have come from elsewhere.
I had a question. Is Hebe still the presumed parent of the H chondrites, or is that just an idea someone had that I picked up somewhere?
That's my understanding that is the most likely candidate, but I think the consensus might be that the H chondrites come from more than one parent body, that there's a lot of similar
Because
bodies.
there is kind of a dynamical way of getting material from Ceres to Hebe, right? I mean, it's a high velocity
transfer orbit.
arrival,
Yeah.
I think, right? But it's possible, dynamically possible, right?
That I don't know. In any way, I would think that the resonances have been scrambled in billions of years.
Right. Yeah.
Steve, I'll remind you that 45% of H chondrites, particularly H4 and H5, have the same cosmic ray exposure age. And so there can't be too many parent bodies involved there. And the H3s, and they look like a really nice continuous sequence. So I'm skeptical that there's more than one that's a major contributor.
Yeah, I agree. I think 6 Hebe definitely is thought to be the parent body, and then my take on the field is that there's 50-50 chance there's multiple H chondrites, but it's not like hundreds. It's
So I've got a comment to make, if I can. You guys are here. So a long time ago, he called me and said, I got this meteorite with Zag with halite in it. He said that he cut it dry because of Monaghan's. He said he found water inside the meteorite when he was cutting it. And if you look at Zag, even really freshly broken pieces, they're kind of rusty looking, right? And so on Ceres, you have potentially hydrohalite on the surface, right? And that's basically halite with the water attached to it, which is only stable at freezing temperatures. So if you had a meteor, if you had hydrohalite in a sample and it arrived at Earth above 0 degrees C, it's going to melt to brine plus halite crystals, which is kind of what we saw in Zag. I mean, the halite crystals weren't new halite crystals; they were purple old ones, right? But there could have been, hydrohalite in that sample, which resulted in brine, liquid brine, being present in the meteorite on the ground in Morocco. So are there other meteorites people have cut that they've cut or broken it dry and gee, it looks like it had water inside? One of any other report like that? I've never seen that, but I haven't broken many meteorites, fresh ones open, without sawing it, or even with a dry blade to know that. No one else has seen that. I mean,
well, I had Weathersfield 82 on my desk less than 24 hours after it fell, but I didn't see any water.
Yeah,
It's an L6.
okay. Right. Okay.
Anyway, I think we're gonna wrap up. It's been an hour. I just want to thank everybody and remind you all that our next lecture, continuing.
Don's hand's still up. You have a question, Don, or you just didn't take it down? Okay.
No, I guess they have. We're going to continue our JSC series here. Mark Fries is going to give us a talk on April 16th next time on rapid meteorite recovery in recent meteorite falls. So we're looking for the this JSC duo coming along. I want to thank everybody
Yeah.
for coming today, and I want to thank our speaker for a fascinating talk. And we look forward to our sample return mission from Ceres, which Mike will be proposing soon.
Yeah, good luck.
Okay,
Thanks
thanks,
a
everybody.
lot for your questions. I appreciate it.
Okay. Thank you.
Bye, Alan and Kevin. Bye, Don.
Bye, everybody.
Nick. Bye, Steve. Thanks for your question.
Kevin, time for you to cancel the recording. You're on mute.
Sorry, I'm trying to figure out where the recordings, there it is, stop recording.